Hello, everybody. Welcome back to class. Our final class of the week, Thursday, April 9th. So let me see who's in the chat. Say hello. Good crew so far today. Everybody's right on time. They're excited for what we got lined up for today. Ooh, once I said that, everybody left. Oh, they're still leaving. Navik, right on time as usual. Lauren Turner, hello. Jared and Jax, good to see you. We got a good class lined up for today. Jonathan, thank you for commenting on my YouTube video. I really like when people comment on the videos. Reagan and Jack, welcome to class. Hebert, hello. First time in class, it seems like. I don't recognize the name. Ellie, good to see you. Good to see you again. Hebert, where are you tuning in from? USA? England? Somewhere in Europe? I don't know. Sam, Akil, good to see you. Sup, Akil. The sup always gets me to chuckle. Mexico, great. Well, welcome. Well, it's 10 o'clock, so we could get started. So if anybody has their coffee or water ready and would like to join in on the simultaneous sip, now would be the time to do so. All right, let me see in the chat who joined in on that one. Is that Irish coffee? No, I would get fired if it was Irish coffee. Morning, gang. Sip. Okay, so before we get started, I got to say that was pretty funny. The prank we pulled on Dr. Y yesterday with those comments on her video. She thought they were bots. I had her email me the names of everybody that sent the early ones, but after like 10, the first 10, she deleted them because she thought they were all bots. But I have the names, so don't worry, you're getting your extra credit. But yeah, she was not sure what hit her, and I told her, yeah, I gave my class your videos, so because it's a good question, and she thought it was funny. But yeah, so if your comment is not appearing on her video, don't be worried. I have all the names written down. Mine was done at 9:50. Yeah, so it's still there. The ones that were deleted were the really early ones, which were sad because some were pretty funny. Okay. Yeah. So yesterday, what did we do? We did anti-derivatives, which we took a function and we went backwards, right? We asked which function's derivative gives us f. Today, we're going to do something that on the surface appears totally different. Okay, but maybe, and no spoilers in the chat, please, maybe there's quite a powerful relation between what we're going to do today and what we did yesterday. Okay, so this is chapter 4, integrals. Okay, so today we're working on integrals. We'll start with 4.1. which is areas and distances. Okay, and now again, this class, okay, this is not to scare you, but today's lesson it's not going to be quite at the level of the epsilon delta stuff. It's a little bit easier than that, but it's one of the harder lessons of the semester. So, and we're doing fine in terms of our pace. So, if you need me to slow down, just tell me in the chat to slow down and go over the material again, and I'll happily do it. Okay, because this is a kind of an important concept we're going to go over. But yeah, there are going to be some Greek letters that appear, and yeah, so just a little heads up. Okay, so but feel free to slow me down if you need me to slow down. So we begin by trying to solve the area problem. Which is find the area of the region S. That lies under a curve Okay, so let's sketch a picture of what we're trying to do here. Okay, so we have some curve, y equals f of x, that's the top boundary. And we want to find the region of this shape. Okay, that's what we're trying to do here. Okay, so the question is at least easy to state. Find the area of this shape. But we'll see, we're going to need a couple of techniques. Okay, so since the top of the region is curved, okay, hold on, before we get going, can any of you hear the music that's being blasted by my neighbors right now? It sounds like a rock concert's going on. So if you hear rock and roll in the background, I apologize, but there's nothing I could do. Okay, since the top of the region is curved, this problem is hard. Right, we can't, like we don't have any tools from geometry, like our high school geometry class. All right, nope, good. All right, so good. Only I could hear it. To find the area of this region. So this question is much easier if we're dealing with regions that have straight lines. Right, so for example, if we had a rectangle that was length L and width W, we could find its area. Or a triangle, we could also find its area, right? Here, the area is length times width. With a triangle, when we have the base and the height, it's 1/2 base times height. And even if we have a region, let's say like this, some just pentagon, we could take our region and break it up into some smaller triangles and just add up their areas. Right, so in this pentagon case, sure, we don't have like a nice formula like this, but we could say that its area is equal to A1 plus A2 plus A3. And we could use whatever techniques we have to find the areas of these three triangles. So we add them all up, and that's a way to get the area of that pentagon. So in general, when our area is a polygon, what we could do is just divide it up into a bunch of triangles and add up those areas. Unfortunately, this technique doesn't work, though, with curved regions, right? We could approximate breaking it up into triangles, but it's not going to be perfect. So this won't work for curved regions. And so what we're going to do, again, we're going to just approximate the area, but instead of using triangles, since it's going to be an approximation anyway, we're going to use rectangles just because the formula is a little bit easier to work with. Okay, so for curved regions, we're going to approximate this area. I mean, eventually we're going to learn how to get an exact area, but for now, we're going to approximate the area by splitting it into rectangles. So let's take a look at what I mean here. So for example, and now I don't expect you to know how to do this yet, so we're just going to walk through it together. Use rectangles to estimate the area under the parabola y equals x squared from 0 to 1. Okay, so basically what we want to do is we want to find the area of this region. Okay, so by a show of thumbs up or thumbs down, do we at least understand what the question is asking? Maybe we don't understand how to do the question yet, but do we understand what the goal of the question is? Approximate the area of this region. Okay. So a few people are saying thumbs up or smiley face. Great. So what we could do we could break up this region into 4 rectangles. And I picked 4 just because it's a small number, but not too small. So we could break up S, our region here, into 4 rectangles of equal width. Okay, there's 2 ways we could do this, or there's many ways, but for instance, there's 2 ways we could do this. Okay, so let's break up our x-axis here into quarters. And we're going to use, here we're going to say the heights of our rectangles are determined by the curve at the right endpoint of our intervals. Okay, so this would be heights determined and so what that would look like, we go to each one of our subintervals, we go to its right endpoint, we go up to the curve, and we have a rectangle whose height is given by the y value of the curve at the right endpoint, and its width is, well, we'll have to figure out the width in a second. Okay, and so we do this. Okay, so is this clear what we did? We found the y value at each of the right endpoints, and we made a rectangle that's tall, that the height is given by the y value at the endpoint, and its width is something we'll have to figure out eventually. But we could approximate the area of S by now adding up the areas of these rectangles. How did we determine to use 4 rectangles? We just picked 4 for the purpose of having a small number, but big enough to kind of see what's happening here. Eventually, our goal is to make the number of rectangles approach infinity. Okay, so eventually we're going to have some techniques to say, well, let's not have 4 rectangles, let's have 1,000,000 rectangles, or a billion rectangles. But yes, 4 is a good way to draw it on the board. So that's how we picked 4. It was kind of given to us in the question, or I gave it to us. Okay, and now similarly, we could do the same thing with the left endpoints. So the left endpoint of this first subinterval is 0, and its y value is also 0. So our first rectangle is actually has no height. That's okay though. The next one so this is the left endpoint. Okay, so you can see here in this example, when we use right endpoints, we actually got too much area. Our approximation will be too high. When we use left endpoints, our approximation is going to be too low. So this will give us a kind of a range of where our solution is going to be. Before I move on, still good, or need me to repeat some stuff? The width of each rectangle is 1/4. Okay, how did I get 1/4? Well, the width of the entire thing is 1, right? We go from 0 to 1. And we broke it up 4 times, so each one has width 4. Why do we use right and left endpoints? Are they both for height? Yeah, so here we're just kind of just playing around with this to kind of get a sense of what's going to be happening behind the scene. Here we use right endpoints, that determines our height. And when we did that, we got an overestimate. And here we determined our heights with the left endpoints, and it happened to be an underestimate. But yeah, so we could pick, and there's other ways to pick, but these are just 2 ways to pick. We picked right endpoints, it gave us this picture. With left endpoints, it gave us that picture. And the endpoints come from these little subintervals we're dealing with here. Okay. So again, just keep firing with the questions, but I'm going to keep moving along a little bit. Okay, so the area So to get the area with the right endpoints, which we'll call R4, R for the word right and 4 for the number of rectangles. Well, it's the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle plus the area of the fourth rectangle. So the width of the first rectangle is 1/4. And its height is the function value at the right endpoint. And the right endpoint here is 1/4. So that's the area of the first rectangle. The area of the second rectangle, again, it has the same width, 1/4. And its height is the function value at the right endpoint here. That's the x value 1/2. So it's, and we could do this for all 4 of the rectangles. So width times height, width times height, width times, add up all these areas, and that's how we're going to approximate the area under the curve. Okay, what is our function? Our function was y equals x squared. So our area with right endpoints is this number, which we would plug into a calculator, which works out to be 0.46875. Okay, so that's just from using a calculator or a computer. Okay, so are we good? Or do you have any questions about how we approximated the area using right endpoints? Because now we're going to go through and just do the same thing with left endpoints. So ask any questions you may have. Give you a couple of seconds to type them in, and I'll move on to left endpoints. Why did we square the values again? Okay, so that comes from the fact that our function is the function y equals x squared. So if we had a different function here, we would do different things to the values. Yeah, so f, right, our function f of x is equal to x squared. So f of 1/4 is 1/4 squared. F of 1/2 is 1/2 squared. Right, so if we were looking at a different curve, we would be doing different things to our numbers. Why is 1/4 in front of all the values? That's the width of each of these rectangles. Each of these rectangles has width 1/4, right? Because the whole region has width 1, and we broke it up into 4 small regions. Yeah, Greg, because there are 4 rectangles, so it's the width of the whole region, which is 1, divided by the number of rectangles, which is 4. Also, late sip. Nice. Sorry. So let's do this again with the left endpoints. So here we'll call it L4 for the left endpoints. And again, let's just find the areas of each of these rectangles. So the left endpoint of the first subrectangle is x equals 0. Its width is 1/4. So width times its height, which is f of 0. Plus, now we'll go to the next one. Its width is still 1/4. The left endpoint of the second subinterval is the x value 1/4. For the third subinterval, its left endpoint is x equals 1/2. Notice each time we go up by 1/4 for our endpoints. We go up by the width for each of our endpoints. And the last one is 1/4 f of 3/4. Right? Its x value is 3/4, and its height is f of 3/4. Its height is f of 3/4. Its width is 1/4. That's its area. Again, our function is f of x equals x squared. So our function is f of x equals x squared. So evaluating the function at each of these x values is just the same thing as squaring them all. And then, yeah, we could plug this into a calculator. And so just based on our drawing, we see that with the right endpoints, we have an overestimate. And with the left endpoints, we have an underestimate. Right? With the right endpoints, we have all this region above the curve that we're counting. And here we have all this region below the curve that we're missing. So we can conclude that the area of the whole region lies somewhere between these two numbers. Okay, so our approximation for the area of this region maybe is like 0.3, for instance, somewhere right in the middle of those two numbers. But what we could do to get a better estimate is we could just bump up the number of rectangles, right? We did 4 because it's kind of easy enough to do by hand, but it's 2020. We got to use a computer every once in a while. So we could bump up the number of rectangles and improve our approximation. So we could repeat this process with more rectangles to improve our approximation. In fact, what we're going to do is we're going to take the limit as the number of rectangles goes to infinity, and that's going to be the area under the curve. Would the whole process to find the area be the same even with more rectangles? Yeah, it's going to be exactly the same. So the number of rectangles would just be, right, the number of terms in this sum. So what would change if we had more rectangles? Well, the width of each rectangle would get smaller, and we'd have different heights we'd be dealing with. But yeah, the process is exactly the same for an approximation with more rectangles. Yeah, so we picked 4 because it's small enough to do by hand, but big enough to kind of see what's happening behind the scenes. Okay, so what we're going to do, oh my gosh, this example is taking a really long time. Okay, so if I go past 10:40, please stop me because we have to take this quiz. Wow, okay. When you're in the zone, you just kind of lose track of time. Okay, let's look at this example. Let's find the exact area. So what we're going to do, instead of having 4 rectangles, we're going to take the limit as the number of rectangles goes to infinity. So for the region S in the previous example, show that the sum of the areas of the upper approximating rectangles, so our upper bound, is 1/3. Okay, what is the quiz on? It's on optimization. That is the limit as n goes to infinity of Rn is equal to 1/3. Okay, so we want to show that this limit, the limit as n goes to infinity of our approximation using right endpoints, gives us 1/3. Okay, so let's talk through how to do this together. Again, today's just like the first day we're seeing it. After the weekend, because I know you guys are going to focus on this type of question a lot over the weekend, we'll have plenty of examples for you to work out on your own. Okay. So each rectangle, right? If we're gonna say we have n rectangles. So let n the number of rectangles. Right, we're going to take the limit as the number of rectangles goes to infinity. Each rectangle has width 1/n. Okay? So each rectangle has width 1/n. The heights, or the right endpoints, are x equals 1/n. It's like 1/4. And then we go another 1/n. So 2/n, 3/n, all the way up to n/n. So these are the right endpoints. So in our example we just looked at, n was equal to 4. So it was 1/4, 2/4, 3/4, and 4/4. But you can imagine if we had more rectangles, this is still going to work. So our right approximation is equal to 1/n times f of 1/n plus 1/n times f of 2/n plus 1/n f of n/n. And since our function was f of x equals x squared, instead of having f of 2/n, we could have 2/n squared. We could factor out a 1/n and a 1/n squared from each of these terms. So this sum is really 1/n to the third times And then what's left over would be 1 squared plus 2 squared all the way up to n squared. Okay, and now we're going to use an identity that I would provide to you on a test or a quiz. This sum here, the sum of the first n squares. Now, I would be shocked if you knew why this was true, or if you knew this in the first place. So just trust me that this is true. We'll talk about it in more detail next week. The sum of the first n squares is n times n plus 1 times 2n plus 1 all over 6. Okay, so instead of having a sum with n terms, we have this product with 3 terms. How did I factor out an n to the third? Well, each term has a 1 over n, and each term also has a 1 over n squared. So you could factor out a 1 over n to the third. And this becomes, so since we could replace this sum with this product, this becomes 1 over n to the third times n plus 1, 2n plus 1, all over 6. Again, I would give you this identity, so don't be stressing out about this. Okay, let me finish this up. You're free to start the quiz now if you'd like. This is going to go onto YouTube, but I'm going to stay here and finish the question. The quiz should be quick. Now the question says evaluate this limit. So let's do the limit as n goes to infinity of n plus 1, 2n plus 1 over 6n to the third. And this is a rational function. And we want to find basically we're trying to find its horizontal asymptote. And the way we could do that is, well, I mean, there's a few tricks. We could multiply the numerator and denominator by 1 over n to the largest power that appears in the denominator. Or we could just read off right? This is the same thing as the limit. Goes to infinity. We could multiply this out and get 2n to the third plus 3n squared plus n. And so since they have the same power in the numerator and the denominator, it just works out to be the quotient of their leading terms, so which is equal to 2/6, which is equal to 1/3. Okay, so I know this was a lot. So you'll have some identities when we're trying to find these areas by hand. But yeah, so what's going to happen here is eventually we're going to just be trying to evaluate some sort of limit as n goes to infinity and see what we get. In this case, we ended up getting 1/3. Yeah, I'm going to stay around for as long as you need to ask questions. But this is just day 1 of these integrals. Okay, so if you're confused, that's perfectly fine. I'm sure all of your classmates are also confused. But yeah, the idea here is we're going to find the area under the curve by just breaking it up into a bunch of small rectangles and adding them up. Okay, so that's the big idea. Yeah, so that's a good place to stop. We'll obviously talk a lot more about this on Tuesday. But go take your quiz now. Submit it to Canvas. PDF, please try to figure out how to use the PDF. Yeah, hit the like button before you leave. And yeah, I got nothing else to say. I'll stay around to answer any questions if you have any, but don't be stressed if this is I wish class was longer. Yeah, me too. Don't be stressed if this is confusing to you right now, because it's confusing to everybody. Well, you'll start to see it a little bit better once we do a little bit more of it. Okay, well, so have a good weekend. I'll stay here for a few more minutes if anybody has any questions, but yeah, good luck on the quiz. You'll do fine. Thank you for the class. Greetings from Alabama. Yeah, no problem. Welcome to class. I'm glad you came. Dr. Bevy 5. Happy weekend, Hebert. Avik, and you have a good weekend. Thank you. Thank you. Okay, well, if nobody has any questions, I'm going to sign out. Yeah, we'll see you on Tuesday. We'll pick up with where we left off. All right, bye-bye.